Hi, and welcome back to Hacker101. This is the first in a three-part series on cryptography. In this session, we're going to run through the basics of crypto from simple to complex. Every major construction you need to know about is covered here, so let's jump right in. You may be familiar with XOR, or exclusive OR. This bitwise operator compares two bits, A and B, and outputs a new one. If A or B are 1, but not both, the result is 1. Otherwise, it's a 0. XOR has a property that makes it critical for crypto. It's self-reversing. If you have D equals A XOR B, then A equals D XOR B, and B equals D XOR A. Given this, we can actually produce a simple, absolutely perfect cryptography scheme. Generate a key of n bits of true random data, then XOR each of the key bits with the corresponding bit of plaintext. This produces a perfectly encrypted ciphertext blob of n bits length. To decrypt, simply XOR the ciphertext with the key again. You may recognize this as a one-time pad. If you only ever use a given key once without repeating it in any way, this is fundamentally unbreakable. That is the one-time part of it though, and obviously we don't want to have to give a huge pre-generated key to every person we want to communicate with. That's why OTPs aren't used on a daily basis. Since we don't want to do this kind of key sharing, how can we safely share data with all parties? The field of cryptography really exists to answer that question, and to poke holes in the answers. We can break down the types of ciphers in use today into two families. Symmetric ciphers, where both sides use the same key, and asymmetric ciphers, where each side has a private key and the other side's public key. Symmetric ciphers can be further split into two subtypes: stream ciphers working byte by byte, and block ciphers working block by block. In stream ciphers, we work byte by byte. A common example is RC4, often used in SSL. The construction is pretty straightforward, with the core essentially being a random number generator, whose seed is actually your encryption key. Read a byte from the RNG, XOR it with the plaintext, and store that as the next byte of ciphertext. To decrypt it, just generate the same stream by using the same key, the seed, and XOR that stream with the ciphertext. The fact that stream cipher operations are identical for both encryption and decryption makes them substantially simpler than most other types of ciphers. Given this definition, we can construct a simple stream cipher by choosing a given PRNG and seeding it with our key on both sides. The strength of the algorithm then lies solely on the quality of the randomness. The better the quality of that output, the stronger our cipher. Block ciphers are perhaps more familiar to most people. AES, DES, 3DES, 2FISH, and other very common algorithms are all block ciphers. In a block cipher, you split your data into some number of n byte blocks, each of which gets encrypted separately. Because data doesn't always fall on n byte boundaries, we have to have a way of safely adding padding. Additionally, the encryption and decryption processes are usually not the same, unlike stream ciphers. Because of the blockwise encryption nature of block ciphers, many modes of operation exist to make them more secure or to serve various goals. Let's talk about two of them. In electronic codebook mode, better known as ECB, each plaintext block gets encrypted with the key to produce a ciphertext block. That means that if you have two blocks with the same ciphertext, you know they must have the same plaintext. That may not seem like a big deal, but take a look at what happens if you encrypt an image of tux with DES in ECB mode. While the image doesn't exactly look perfect, it's certainly recognizable. Any solid area of color that doesn't cross a block boundary is essentially completely visible. Cipher blockchaining mode, or CBC, is perhaps the most common form you'll see. With CBC, each plaintext block is XORed with the ciphertext of the previous block prior to encryption. The opposite is performed for decryption, and the first block is XORed with an initialization vector, or IV. Because the blocks are chained in this way, flipping one bit of ciphertext in block 0 will flip the same bit position in block 1 upon decryption. This property makes for some fun bugs you'll see in the next session. Asymmetric ciphers are quite a bit different. With these, each party has a public key and a private key, often called a key pair. RSA is a common example of this class of ciphers. Asymmetric ciphers are used both for encryption and for signing, a process that allows one party to validate that a message originated from another. Generally, these are not used for encrypting bulk data directly. This is due to performance concerns and complexity. Rather, you'll typically generate a random key for a symmetric cipher, then encrypt that key with your asymmetric cipher for transmission. For instance, if Alice wants to send a secure message to Bob, she'll encrypt the message with a random symmetric key, then encrypt that key with Bob's public key, and then send both the ciphertext of the message along with the encrypted key. On the receiving end, Bob decrypts the key with his private key, then decrypts the message using that symmetric key. Hashes are another important construct, but it should be noted that these are not encryption algorithms. Rather, they are a construct that takes in an arbitrary blob of data of any size and generates a fixed size output. MD5, SHA-1, SHA-256, and others are all examples of hashes. Because they take any amount of data and reduce it to a fixed number of bits, all hash algorithms have collisions, which is to say an infinite number of inputs will generate any given output hash. However, the strength of an algorithm is in how difficult it is to find such collisions. A hash on its own is really only useful for one thing in crypto, ensuring the integrity of data. If you're given a blob of data and its hash, it's trivial to confirm that the data has not been tampered with. However, it doesn't ensure that the hash itself hasn't been manipulated, nor does it authenticate a sender. MACs, message authentication codes, are generally based on hashes, although others do exist, for instance CMAC using a block cipher, and these allow for authentication of messages. That is, if you're given a MAC, you can ensure that neither the data nor the MAC itself have been manipulated. This is because with a MAC, you have a shared key that's used for the construction and validation of the MAC. Without that, it's not possible to create a valid MAC. The most well-known MAC is called HMAC, for hash-based MAC. It's based upon a hash algorithm of your choosing, and it's a fairly straightforward construct. Hash the shared key along with the message, then hash that resulting hash with the shared key again. This is a minor simplification of how it really works, but that's the key premise. In the next video, we're going to be talking about several interesting cryptographic attacks, building upon the concepts we've gone over in this session. As always, thanks for watching, and happy breaking!